Hello. In this second video of this section on resting membrane potential, we will look at the origin of the resting membrane potential. We will define the resting membrane potential and try to understand how it comes about that cell membranes are charged. So, as we discussed earlier, cell membranes are polarized. There is a charge separation. So the questions that arise are, how does the membrane become polarized, and specifically, how does an inside negative resting membrane potential develop across cell membranes, particularly the cell membranes of excitable cells like neurons or muscle cells. To understand the origin of resting membrane potential, let's begin by considering a hypothetical scenario. Think of a kind of a tank with two compartments, a compartment on the left hand side and a compartment on the right hand side, which is separated by a barrier. Both the compartments are filled with a solution of potassium chloride. However, the solution on the left side is at a much higher concentration compared to the solution on the right side. As you can see, the greater density of ions here compared to the density of ions on this side. Then imagine we have a voltmeter, the kind of voltmeter that we encountered earlier, with one of its electrode, let us say the recording electrode, in the left hand compartment and the other reference electrode in the right hand compartment. Therefore, this voltmeter would record differences between the recording electrode, that is in the left hand compartment, and the reference electrode, which is in the right hand compartment. In other words, it would record the potential difference between the two compartments across this barrier. Now, instead of having a solid barrier, let us imagine that this barrier is actually a membrane, particularly a semi-permeable membrane, which is permeable only to potassium ions and to no other ions. Now, in this state, the voltmeter would be recording a zero potential in the beginning, because if you look at the two compartments carefully, the number of positive charges, the ones shown in blue here, are almost exactly equal to the number of negative charges that shown in green here. Therefore, within a compartment there is electrical neutrality. Within this compartment too there is electrical neutrality. Though there are fewer potassium ions and fewer chloride ions, their numbers are almost exactly matched, and therefore there is electrical neutrality within this compartment. Therefore, the potential here would be the same as potential here, and therefore the voltmeter would record a zero potential. However, the moment the membrane becomes permeable, or we consider a membrane that is permeable to potassium, specifically to potassium, then things change quickly. Now, what happens is, because there are far more potassium ions in a given volume of fluid here in the left hand compartment compared to the right hand compartment, there is a gradient, a concentration gradient for potassium ions from the left hand side to the right hand side. And because potassium can cross this membrane, potassium ions which are at a higher concentration on the left hand side will quickly diffuse into the right hand side, where there is a lower concentration of potassium ions. So, the presence of this chemical gradient or concentration gradient drives potassium ions rapidly across the semi-permeable membrane from the left hand side to the right hand side. And as this happens, there are two things that we need to note. One, the concentration of potassium rises on the right hand side and correspondingly falls on the left hand side as more and more potassium ions move across the membrane. Therefore, in effect, the concentration gradient or the chemical gradient is reducing with every passing moment. Also, with every potassium ion that moves from the left hand side to the right hand side, what is happening is that a positive charge is leaving the left hand compartment and entering the right hand compartment. As a positive charge, as a potassium ion moves from the left to the right across the membrane, it is leaving behind unbalanced, unchaperoned, unaccompanied negative ion. So very quickly, it so happens that on the left side, the side from which the potassium ions are exiting, you have marginally fewer positive charges and correspondingly a larger number of negative charges. And on the right hand side, into which the potassium ions are entering, you get a marginal surplus of positive charges and a deficit of negative charges. Therefore, you can see that there is a separation of charges across the membrane. On one side, there is a marginal surplus of negative ions, and on the other side, there is a marginal surplus of positive ions. So this leads to development of an electrical gradient. Now the electrical gradient, as you would notice, is from the side which is more positive to the side which is more negative. That is by convention, isn't it? And therefore the electrical gradient is actually directed opposite to that of a chemical gradient. As more and more potassium ions leave the left hand side and enter the right hand side, there is greater positivity here, and gradually this greater positivity repels further potassium ions from entering the right hand side. So on one hand, you have a chemical gradient which is pushing potassium ions from the left to the right, but that movement itself creates an electrical gradient, and that electrical gradient opposes further movement of potassium from left to right. So with ongoing diffusion of potassium from left to right down the chemical gradient, as I pointed out earlier, the chemical gradient itself becomes smaller, and with ongoing diffusion from left to right, the electrical gradient continues to grow. Therefore, you have a scenario where within a very brief time, given the diffusion of ions rapidly, the chemical gradient shrinks, the electrical gradient becomes larger and larger, and you soon reach a situation where the magnitude of the chemical gradient is equaled by the magnitude of the electrical gradient, but it is in a direction opposite to that of the chemical gradient. Once that situation is reached, the number of potassium ions that move down the chemical gradient would be more or less equal to the number of potassium ions that move from the right to the left down the electrical gradient. And we reach a situation what is referred to as equilibrium. And the potential at which equilibrium is reached is referred to as equilibrium potential. So the equilibrium potential for any ion is the potential at which the ionic flux down the concentration gradient is equal to the ionic flux down the electric gradient. Remember, the electric gradient is directed opposite to that of the concentration gradient, and therefore ionic flux down the chemical gradient is equal but opposite to that of the ionic flux down the electrical gradient. So in this state of equilibrium, there is no net flux of ions across the membrane. There are of course potassium ions moving from the left to the right down the chemical gradient, and there are of course potassium ions moving from the right to the left down the electrical gradient, but they are more or less equal in number. The movement is more or less equal in either direction, and therefore there is no net flux of ions across the membrane. Now, what is the magnitude of this equilibrium potential? what determines the magnitude of the equilibrium potential for any given ion which is diffusing across a semi-permeable membrane. Now, to understand this in a very simple way, look at this scenario, which is very similar to what we described earlier, but I'm just now putting numbers onto it. So on the left hand side, you have a 100 milli equivalent per liter solution of potassium chloride, and on the right hand side we have a 10 milli equivalent per liter solution of potassium chloride. Therefore, there is a 10 times chemical gradient from left to right, and as expected there will be movement of potassium ions from left to right down the chemical gradient, creating an electrical gradient that is directed in the opposite direction, and ultimately the electrical gradient becomes as large as the chemical gradient, and there is an equilibrium reached, and the potential at which this equilibrium reach is the equilibrium potential for this system. Now, just look at the second scenario, where the concentration of potassium chloride on the left hand side is 1000 milliequivalents per liter, and on the right hand side remains 10 milliequivalents per liter. So here you have 100-fold or 100 times chemical gradient from left to right. Here too there will be diffusion, but here, because of the larger concentration difference, the concentration difference 1000 versus 10 is much more than what we had earlier, 100 minus 10. Therefore, the chemical gradient is much larger in this case compared to the previous case, and therefore the movement of ions down the chemical gradient will continue for a longer time, and it continues even after a substantial amount of electrical gradient is produced, and the electrical gradient at which the movement of ions due to the chemical gradient is countered has to be larger than in the previous case. Therefore, the electrical gradient, the electrical potential at which equilibrium is achieved here is at a higher level. That is, the magnitude of the equilibrium potential is going to be larger. So this drives home the simple point that the equilibrium potential, the potential at which there is no net flux of ions, is actually determined by the difference in the concentration of ions on either side of the membrane. Larger the difference, greater the equilibrium potential. Smaller the difference, lesser the equilibrium potential. So, in fact, if you to summarize this, one would say that the magnitude of the equilibrium potential depends on the difference in the concentration of ions across the membrane. For cations, it is negative with respect to the direction of the concentration gradient, like we saw in the example for potassium, and for positively charged ions, that is, for negatively charged ions, that is anions, the equilibrium potential will be positive with respect to the direction of the concentration gradient. Now, this was actually formulated almost 100 years ago by Nernst, and I think many of you would be familiar with the Nernst equation, which is actually a formulation of what we have discussed in a descriptive way over the last few minutes. So what does Nernst equation say? In a situation where there is a concentration gradient, so there is a concentration, say Ci on one side and Co, that is internal versus outside, inside versus outside. If there is a concentration gradient of this nature, the movement of ions from A to B would be determined by this concentration gradient, and then that movement itself would generate an electrical potential which would be in the opposite direction to that of the concentration gradient. And as I said earlier, at equilibrium, the movement due to the chemical gradient, the concentration gradient, would be equal to the movement due to the electrical potential. And Nernst demonstrated that the equilibrium potential would be proportional to the logarithm of the ratios of the ions on either side of the membrane. So in this case, the ratio of C outside to C inside, the logarithm of that would determine the equilibrium potential. There are a few constants in this equation. For example, the gas constant, the absolute temperature in Kelvin. Z is the valence of the ion under consideration. So for a cation like potassium, it would be positive. and for anion like chloride will be negative, and F is Faraday's constant, Faraday's electrical constant. So Nernst equation gives us a way of estimating or predicting the equilibrium potential if we know the concentration of ions on either side of the membrane. So if you apply this to a cell, if you know the concentration of an ion inside the cell and outside the cell, for example, if you know the concentration of potassium in the extracellular fluid that is outside the cell, and if you know the concentration of potassium in the intracellular fluid that is inside the cell, then one can calculate the equilibrium potential for potassium across the membrane by applying Nernst equation. It would simply be roughly 60 into the logarithm of the ratio of potassium outside to inside. This simplified formula is in a logarithm to the base 10, and all these constants have been incorporated in this number 60. They have been simplified to this number 60. So a very simple formula to remember: equilibrium potential is equal to 60 into log to the base 10 of the ratio of the ion outside to inside. So what does it take to have a potential across a membrane? I think from the previous discussion it becomes clear that we need to have a concentration gradient to drive the ion across the membrane, and of course the membrane should be permeable to that ion. A membrane which is impermeable to an ion will of course not develop potential attributable to that ion, because ions are simply not allowed to cross the membrane. So concentration gradient and permeability is what it takes to have a potential across the membrane. Thank you.